In the seventh tip, we want to describe how to work with an angle of depression. In an angle of depression, the idea is that you have an elevated observer who takes a sighting from where he is to someplace down below and measures this angle between the horizontal and the line of sight. And then we want to compute some distances or other angles in the problem. In this case, we have a radio tower, an observer up at the top, sighting down to a point on the ground, and the observer finds that this angle of depression is 52 degrees and wants to answer two questions. How far is it from the middle of the base of the tower out to this point? And if it wanted to stretch a cable across here through this line of sight, how long would the cable have to be? If we simply abstract this a little bit, you can see that this is a kind of problem that we've already solved. We have a right triangle, and it's important that we're choosing this point directly beneath the observer, not the side of the tower, so that we have a right angle here. And we have one side of this right triangle, 150, and we know an angle, but the angle is not in the triangle, but that's actually not a big problem. What you want to do is just sort of fill out the diagram by making a copy of this triangle up here, just flipped upside down and turned around, so that this is a right angle here, this is a right angle here, and all the way across. We have a rectangle then, and you can probably see pretty quickly that this angle, 52 degrees, is the same as this angle, 52 degrees. Another way of looking at that is we have two parallel lines and a line that cuts across them. There is a theorem in elementary geometry that tells us that these, what are known as alternate interior angles, have to be equal. So this angle and this angle are the same. Once we know that, then we know that of the 180 in this triangle down here, we've used 90 for the right angle, so 90 remains, and we used up 52 on this interior angle, so this angle up here must be 38, so that these three will sum up to be 180. All right, we know all three angles, and we know one side. What we would like to be able to do is to compute this distance along the line of sight. We'll call that C. Because, well, it's a hypotenuse of a right triangle. We usually call that C. Or you could think of it as the length of the cable that we're trying to compute here. And I'll call this X because it's a horizontal distance, and we often call that X. Okay, let's see if we could compute one of these two. How about this? We know that the tangent of 52 degrees is the length of the opposite side divided by the length of the adjacent side. So we could multiply both sides by x to get the x up here, and divide both sides of this equation by tangent of 52 to bring the tangent of 52 degrees down here. And this now becomes a calculator problem. I've got 150 divided by the tangent of 52 degrees, and this is approximately 117. Now we're going to carry several digits so that we can use this calculated value later on without introducing too much round-off error. So we're going to take this to be 117.1928. All right, that gets us this distance, and now we're after the length of the cable. The length of the cable we could compute with a trig function again, or we could use this with the Pythagorean theorem. Why don't we do a trig function, since we won't have to rely on a computed value then to get this one. So the sine of 52 degrees is the opposite side over the hypotenuse. And same thing as before, multiply through by c, divide through by the sine of 52. And we'll use our calculator to estimate that. And we get 190.3527. So there is our approximations for the length of the cable, about 190 feet, a little bit more, and this distance from the base, center of the base of the tower, would be 117, about 0.19.